Section: Introduction. In this section, we explore how language models can generate large amounts of text based on their training data. We aim to understand where in the model's weights and internal mechanisms the memorized paragraphs are stored. Our focus is on the GPT-Neo 125M model trained on the PILE dataset. We start by defining a memorized paragraph as a sequence of 100 tokens where the model accurately predicts the next 50 tokens given the first 50 tokens. We share these memorized paragraphs and our analysis code. By comparing memorized and non-memorized paragraphs, we observe that perturbing individual tokens in a memorized paragraph is more challenging than in a non-memorized one. Even when perturbed, the memorized paragraphs still make sense and can be seen as alternative versions. We investigate when the model accesses memorized information within a paragraph and how this information is stored in the model's parameters. By modifying a contrastive objective, we can fine-tune the model to reduce memorization while keeping non-memorized paragraphs unchanged. We find that unlearning memorized information is easier than editing it. One specific component that stands out in the model is Attention Head 2 in Layer 1, which focuses on rare tokens in the token distribution. Our experiments also include activation patching and gradients. In terms of related work, we connect research on language model memorization, interpretability, and editing. Previous studies have examined how much and which training data paragraphs are memorized by models like GPT-Neo. We focus on understanding how the model memorizes information and compare different localization methods. Our work differs from studies on model behavior within and outside the training data, which is crucial for privacy concerns like membership inference attack. We also delve into interpreting how models memorize information using gradient-based methods and draw insights from activation patching. Furthermore, we investigate model editing and unlearning by fine-tuning specific parameters related to memorization. Our findings align with previous research on the distribution of memorization components across layers. The editing process involves finding alternative ways to express facts and adjusting the model accordingly. This work is related to language model watermarking and understanding model behavior. Section Summary. In this section, we delve into the localization of memorized paragraphs within language models, focusing on the GPT-Neo 125M model trained on the PILE dataset. By identifying memorized paragraphs and perturbing their prefixes, we reveal that memorization triggers can be pinpointed to specific tokens early in the sequence. Through experiments, we show that unlearning memorized information is easier than editing it, with Attention Head 2 in Layer 1 emerging as a key component in the model's memorization process. Section: Identifying memorized paragraphs. In this section, we focus on a specific model, GPT-Neo 125M, to examine how it memorizes information. The methods we discuss can be applied to any similar model. The GPT-Neo models are designed to be similar to GPT-3 but with some differences in their architecture. These models are trained on a dataset called PILE, which is publicly available and allows us to compare the model's output with its training data. Studies have shown that larger versions of these models tend to memorize more information, but even the smallest variant, GPT-Neo 125M, shows significant memorization behavior in a more manageable computational size. Smaller models are easier to understand and analyze at the level of individual weights. GPT-Neo 125M was trained on the PILE dataset, which consists of a large amount of English text and code. For our study, we used a subset of PILE containing 10,000 unique 100-token paragraphs that were randomly selected. We then processed this subset further to ensure a diverse set of paragraphs for analysis, resulting in 13,450 paragraphs, with the most frequent one appearing 40,382 times in the dataset. We divided the 13,450 PILE paragraphs into two sets: memorized paragraphs, MP, and non-memorized paragraphs, NMP. These sets do not overlap. We used two metrics to make this division: exact match, M, and negative log likelihood, NLL. M measures how well the model's generated tokens match the training set tokens, with a maximum value of 50. NLL calculates the likelihood of the model's predictions for each paragraph. We identified 442 memorized paragraphs with M equal to 50, which stand out from the rest based on both NLL and M values. For non-memorized paragraphs, we selected 12,422 with M values between 0 and 10. While there is some overlap between NLL and M criteria, splitting based on NLL tends to result in more code-related examples with lower diversity, possibly due to fewer alternative options for code-related text. Section Summary. In this section, we focus on identifying memorized paragraphs within the GPT-Neo 125M model. By splitting the PILE dataset into memorized, MP, and non-memorized, NMP, paragraphs based on exact match, M, and negative log likelihood, NLL, metrics, we observe distinct clusters of memorized and non-memorized sets. The smaller GPT-Neo 125M model exhibits significant memorization behavior, making it easier to analyze and visualize individual weights compared to larger model variants. Section: Prefix Token Perturbation. In this section, we explore where interventions disrupt memorization the most by perturbing each token in the prefix one at a time. We replace each token with a random one from the vocabulary and then use the language model to predict the next 50 tokens after a 50-token prefix with a single perturbed token. We measure the impact of the perturbation in terms of NLL and M. We find that certain tokens, even early in the prefix, can lead to a significant drop in M, up to 45. When we look at the mean M drop per token position over multiple trials, we notice that tokens closer to the decoded tokens have a greater influence on the prediction. Interestingly, non-memorized prefix tokens are easier to perturb compared to memorized ones. This suggests that memorized tokens are more ingrained in the model, while non-memorized tokens can easily lead to different but equally likely predictions. We then investigate if there are systematic differences in how the model processes memorized and non-memorized sets. Instead of focusing on token positions, we analyze the model parameters shared across all positions. The model parameters consist of layers and components like attention heads and MLP blocks. We observe differences in parameter gradients between memorized and non-memorized sets, with larger gradients for non-memorized sets. Additionally, we find that there is more gradient flow in lower layers for memorized sets, indicating a smooth shift in gradient patterns for partly memorized paragraphs. Section Summary. In this section, we explore how interventions disrupt memorization in language models by perturbing tokens in the prefix and observing the impact on decoding. We find that certain tokens, even early in the prefix, can significantly affect the model's ability to continue the sequence, with closer tokens having a greater influence. Additionally, we investigate differences in how the model processes memorized and non-memorized sequences by analyzing shared parameters across layers, revealing distinct gradient patterns that suggest varying internal processing mechanisms. Section: Contrastive Objective. In this section, we combine MPS and NMPS in a contrastive objective inspired by a localization method. Our goal is to adjust the memorized continuations of MPS while keeping the model's continuations of NMPS unchanged. This contrastive objective involves increasing the negative log likelihood, NLL, of an individual MPS example and decreasing the Kullback-Leibler, KL, divergence from the model's original continuations of a batch of NMPS examples. The NMPS examples act as a control set to ensure minimal changes to the model. We refer to the original model parameters as theta_0, which are not included in gradient computations. To explore the removal of multiple MPS, we repeat the contrastive objective over 50 different MPS and randomly sampled batches of NMPS, aggregating all gradient computations. We use a tool for implementation and disable gradient computation on certain model components. The parameter gradient scores obtained from the contrastive objective show similar patterns across different settings, highlighting the importance of certain attention head values. Instead of just obtaining attribution scores, we can update the model parameters based on gradients to meet the contrastive objective. This optimization process helps us confirm the significance of localized parameters for memorization. We then focus on unlearning MPS by masking out parameters with low gradient values and fine-tuning the model. Comparing different optimization approaches reveals that focusing on high gradient weights is more effective than random weight masking. Moving on to editing MPS into PMPS, we adjust the contrastive objective to decrease the negative log likelihood on PMPS examples. Results show that unlearning is easier than editing, as observed through perturbing prefixes and analyzing the impact on MPS and NMPS. Further analysis points to the value matrix of attention head 2 in layer 1 as a crucial component for memorization. Instead of computing gradients with respect to parameters, we now calculate gradients with respect to activations. By considering absolute gradients and pooling over dimensions, we obtain attribution scores per layer, model component, and token position. Analyzing the activation gradients reveals the importance of head 2 in layer 1, showing distinct patterns for specific tokens and highlighting its role in memorization. Section Summary. In this section, we combine MPS and NMPS in a contrastive objective to modify memorized continuations of MPS while keeping NMPS continuations intact. By computing gradients based on the contrastive objective, we can selectively unlearn or edit specific model parameters, such as MPS, to observe changes in memorization patterns. The analysis highlights the importance of attention head 2 in layer 1 for memorization tasks and demonstrates the challenges in removing MPS while preserving NMPS in transformer models. Section: Activation Pattern Analysis. In this section, we observe similar patterns in the activations of key query, KQ, attention patterns during the forward pass analysis. The inner product of keys and queries is calculated using softmax and indicates the amount of attention from the current token to previous tokens. We specifically focus on the attention between the first decoded token and the 50 token prefix. Head 2 tends to focus on unique or rare tokens like subscribe and Washington, rather than common tokens like punctuation marks and stop words, unlike heads 3 to 11. When we perturb tokens and analyze activations, we find that rare tokens are crucial for memorization. By ranking tokens based on their frequency in the corpus, we observe that head 2 in layer 1 shows the strongest correlation with rare tokens. This suggests that the model memorizes paragraphs by focusing on their rare words. Our main goal is to locate model components relevant for memorization, but this raises questions about why and how memorization occurs. While we explore unlearning and editing MPS in one section, memorization can also improve performance or be beneficial for certain paragraph types. Future research could investigate how to make a model memorize a non-memorized paragraph. By training a classifier on activations or gradients, we could detect potential memorization during decoding. Additionally, interventions during the forward pass could be explored to influence memorized continuations.